back, everyone. So let's start where we usually do, with a recap of what we were doing last week. I'm just going to quickly post on Twitter. We're live. Okay, so where were we last week? So we had the prior week we had looked at trying to get the GMGC, so the Global Microbial Gene Catalog, annotated in the same way that CheckM2 annotates COGS, annotates KOs from KEGG, and we wanted to do the same for the GMGC using actually only the complete prokaryotic genes, and we were doing that as a way to get a reference. And so the first trial we had done of that, it didn't work so well because we had simply downloaded the GMGC and then ran Diamond on it, which probably would have worked some eventually, but it was just took too long and it was a bit flaky, and so we decided to go and I decided to go and use Jug to do this a little bit differently. And as I mentioned at the time already, this is very much so here's let me just now share my screen. Share my screen. Yeah, so I mentioned at the time this is very much in line with what Jug was designed for, this sort of fan in, fan out. So you have this, so here actually this is from the manuscript, and where is it? Pretty sure we had this type of structure where we have the GMGC, we break it up into chunks, run each chunk independently, and then put everything back together, and then potentially chunks could expand and contract, right? So this is what we did. So we wrote this split FASTA file, takes a FASTA file, I'm just gonna move the microphone, takes a FASTA file, and then outputs a bunch of chunks with a certain number of sequences per chunk. We chose 2 million, and then run Diamond on each of it. And then let's see. So this ran. This ran. Took a little bit, but yeah. So everything is complete, and now we have the. Look, there it is. Right. So. Alright, so next step here is going to be, first of all, let's just get a single file out of this. So here we are going to, right, by the way, let's just see, so here again I'm running Jug shell, puts me in the environment with this. And now I can see, I need to use the value function to load this, and there it is, right? So this, okay, and now I'm going to basically concatenate these, right? So very simple. Concatenate files. Yes, something like this is actually not bad. Alright, so here, so this is what was written by Copilot. It's not what I want to do. Okay, so this is correct import. This is mostly correct, yeah. But let's make this into an argument. And then compressed level 1. So it got this from up here. Normally, before we were building these chunks that were going to be deleted anyway, so that's why it made sense to have compressed level 1. Now let's just use the default, which I believe is 6. and here let's just do something like this. And that's everything in binary mode, no point in okay. So there is the possibility of this getting screwed up if if we're being very defensive. We can. This is a little bit of a dangerous thing because first we write the output. Okay, then we start unlinking, so removing the other files, which I guess is okay. But there is the possibility that if we interrupt the process right here, we've unlinked some of the files, but we haven't really finished everything, and so there is a possibility of getting a screwy situation. But but let's not be too. MGC diamond. Yeah, let's not be too. Yeah, I'm just gonna. Yeah, so. Okay. Okay. So this is gonna take a little bit. But yeah, you can see that this is the. So this is going to take a little bit, but while this runs, we can already start the next step. So the next step would be, so we've been looking at the outputs of actual data. Let's just see what's happening. We're looking at the outputs of actual data, and so we will. And in the past, so in the past we used this code to get the reference sizes. But now we want to use the outputs of the GMGC. So let's do that. Okay. Okay, yeah, okay, I forgot how to do anything with toolbars now. Is this correct? Yeah, it's not correct. It's probably not correct, yes. Let's see. Folders. Read CSV. There, alright, n underscore rows, okay. Okay, there's something here. Read. Sorry. Okay. There's something here that's a little bit off. I actually don't understand exactly what's going on right now. Something here is a bit off. It's a bit off. Polars. Okay, I think this is maybe. Okay, yeah, okay, so this is just being a bit slow, but let's see. Let's wait maybe just a bit longer. I don't know what's going on, to be honest. Let's see what. Okay, alright, I see. Alright, I see Polars seems to be particularly bad at this. So let's just do something. Okay, I just wanted to have start writing the code that does this. Right, so let's see what we. Okay, I guess we need. Does this work? Is this? I guess the only columns we need are these two, and then we want to do this so that. Something like this, yeah. Something, yeah, and now. Okay, now we have the KO there. And now we need to group by the KO and get this, but then, oops, alright, that was jug finishing. We need to group by the KO and get this, and then go from this to the to the size. Right. Okay, so let's, and so for the size we're gonna need to parse the FASTA file. Okay, so let's do one thing at a time. One thing at a time. Okay. So so first we need Unigene AKO set. Okay, let's do a list. And yeah, this is not going to work, but it's more like this. MJC. So we need to do a group by. So polars group by. And then filter. Let's by KO. Then we want to filter. So we polars group by filter. We want to keep only the. We only keep only the ones that have, I don't know what the right number is, but let's say 50 elements. Yes. Yeah. Is this even a thing? Nope. Okay, nope. Polars group by number elements. Okay, so let's set something like this. Elements. Count. Okay, count. Then. Okay, something like this. There's no sort. Okay, so great. Oh, okay. Obviously we hadn't loaded the full thing. Let's load the full thing now. And then we also want to load the this file and get the sizes, basically just get the sizes of the unigenes. So the unigenes is what the GMGC calls its genes. Is so we have a couple of different definitions of what a gene is. So a unigene is this 95% nucleotide clustering. So and they have these names like they have these names like GMGC 10.268328259. So that's the unigene ID. So here, right? Okay, so let's just get the KO there. Yeah, let's say at least 100 just to be. We should probably afterwards do this a little bit nicer, but let's just, so today, if we just get the quick and dirty or version of this, we will be happy. Or at least be productive. Okay, right, so many of them. Okay, 8,000 of them. Okay, let's do this min unigenes per KO. Okay. All right. Does it make any sense, this? Yeah. Okay, so let's say dollars do this. Good. Okay. Okay, actually, here, okay, I'm just gonna reload this because this is correct, what I wrote. I just out of pure curiosity wanted to check how much we're keeping. And then I have and then we're gonna write something like this. Then we're we're gonna write this exactly like this, except here this is a bit too slow. Yeah, so this would actually work, but we're gonna write unigenes. Actually, unigenes is bad. Let's say interesting. Unigenes. Okay, so this will work. Okay, right, so this is what I wanted. So okay, so there we have 39 million. Let's filter, and after we filter we have 39 million. All right, so basically it doesn't filter anything. I mean, it does a couple 100,000, but it's not really net. Okay, but all right. Let's just also something like this. All right, so this would be, all right, so apparently the internet is not so great. Yeah, I'm sorry, this is what QT gives me. I have it's a wired connection, but I'm sorry, somehow this also, sorry, so I'm gonna make myself. Yeah, there's really nothing. Okay, right, so this is now running. It's gonna take a little bit, actually. Demo. Okay, so probably this is probably a bit. Okay, this is probably gonna work. Probably not very efficient, but probably it's gonna work. But potentially, no, not potentially. Eventually, we would obviously want to. We'll obviously want to also figure out a way to compute this one time, and then save the results instead of loading them every time. Because I guess the previous approach, where we were using, since we're waiting, might as well check. So in the previous approach, we were using this file. Let's just see. Okay, now it seems also that the stream is back to high quality. As I said, there's really not much I can do here. This is what QT gives me. And okay, yeah, so before we had 6 million references, now we have 95 million potentially, and then of which about half, so 40 million, are used. So just parsing these big FASTA files. Also, we're now uncompressing the file. So yeah, so this is not going to be. This is not going to be how we do things in the future. We will figure out. Oh, thank you. That's actually nice. Yeah. Okay. Yeah. So you yeah, so this is just in the chat, so I can use .3 split instead of map elements. Okay, that's nice. Yeah, I get, yeah, it's funny because I mean, I've mentioned this before, so I'm switching over from pandas, which is what I was using until, and I'm still mostly using on a day-to-day basis. This is, for this project, I try to use the polars, but pandas, so if I was doing, and some, I guess this is the case where I was a little bit too conservative, thinking, oh, I don't want to write .3.split because that's pandas code, and I'm doing the thing where, you know, it's like this, yeah, like in normal human languages we'd say, you know, it's false friends, right, where you think that a word from one language, you know, and you try to make up the similar sounding word in the other language, but either it means something different or doesn't exist. Right, like if you speak French, you end up and then you speak in English and you say something like I learned her something instead of I taught her something, because in French that's how it works. Yeah, and I guess this is sort of the pandas polars version. But thanks, I will. Okay, right. So let's see. Okay, I wanted to today get this plot, basically the exact same plots we had last week, where we did the z-scores using the UniRef standard, but now using the GMGC standard, because I thought that the GMGC, first of all, would be prokaryotic only. We filtered to only include the complete genes, so it should be cleaner just from that point of view. It should have fewer, it should have fewer outliers, and so because the outliers is what we're looking for. So if it has outliers in the complete genome, or the high quality genome, that's bad, because then we couldn't distinguish from outliers that are due to, you know, errors. Okay. Okay, so what I think I'm gonna do is, so eventually, as I said, eventually this will all move to a separate file. Maybe why is this taking so long? So eventually, maybe I'll just add this as a post-processing to the GMGC outputs, where, you know, as a post-processing, we would just get this table. Ideally, what we want a table that says like K. So right now we have KO and unique gene ID. Maybe we would want to enhance that with KO, unique gene ID, and length of the unigene, and then that could be probably processed really quickly, because then we're really just loading a data file. Okay, so let's okay, so let's just do, okay, since we're alright, let's nodes, 3 nodes. Alright, so today we are no what we want. Okay, so this was the first thing. This is actually quite basic. This is, as I said, this is the sort of thing that Chug really is designed for. Yeah, so Antonio is commenting that, yeah, it takes some time to get used to Polar, but it's worth it. Yeah, this is my hope as well. I mean, some of the operations really are just so much faster. It's sometimes, so apparently, as we were seeing, for example, reading the JZip, reading the JZip is it seems a bit slower because it doesn't as we saw, it takes everything into memory first, but other operations are just so much more worth it. All right, so I think YouTube sort of delays the stream a little bit. Also, before he was complaining to me that my internet was not fast enough, so I think that's all right. So. Okay, alright, so that part is done. Now, get into files, so. This is still running. And imaging. Alright, see, yeah, even I guess it should have been done before, but let's. Okay, that's done. I'm doing actually let's put that on hold for now. Okay, so now we have okay. Okay, so we have that. Let's just double check that these things are correct. AA sizes by KO. Yeah, let's do this, okay? Right, this might be really bad in terms of just efficiency. Sorry, I'm working on. Sorry. Okay, this is good. Right, sorry, I'm trying to do too many things at the same time. Let's clean up. Let's just. Alright, let's just get rid of this. Oh, go back. Anyway, this is one of the reasons why I like working everything on Git. Is because so we can add this sort of random code to files, and then if we like it, we keep it. If if it doesn't spark joy, we just git restore and go back to to what we had that we liked. Okay. Is this too slow? Okay, this is fine. Okay. Okay, let's just see how things look. Okay, and sorry, I'm gonna do this. Sorry, messed it up. Okay, so this is what we've been playing with the last several weeks. So we know we load the results of. Yeah. Okay. All right. And let's hear. Yeah. So we've been doing this map element stuff. Let's try this then. Okay, let's just do one. I guess the problem. All right, so. Split. So I guess we want the split and then the splice, or the slice. Oh. This work? Oh. Yeah, very nice. Okay. Alright, we can. Right, yes, so this works nicely. We would fix the other ones a bit later. Right. Okay, right. So hopefully the z-scores will just look a little bit better than before. In principle, the message should stay the same. Oh. Okay. I mean, yeah, this is, it's not, yeah, this is not only probably much faster, but also just much nicer as well. Okay, number 6. Okay, we don't need this because we've filtered it already. No, I just add it just for. let's just have it. Okay, so here's where we do the z-scoring, and then hopefully, right. Okay. Okay, all right. Okay, yes, probably better. Okay, yeah, I guess before, yeah, just because they were they were using the same database, that would be impossible. That would be, right. They were all part of the database, right? And now, oh, okay, this is actually surprising. Not sure. Yeah, this is surprising. All right, so this is the wild type. So we have a few wild type hits that are really much like -12 z-score. So this is way lower than I expected to be. Okay, still the same. Let's do this. Still a big gap there. Right. Right, I'm just gonna run everything. Okay, yeah, this is actually surprising. Yeah, I did not expect. Yeah, so this is actually the kind of thing that I expected we would be rid of. Yeah, this is normal. Okay, all right. So let's see. But E. coli. So wild type -13. Oh, sorry, -2. That 13, and then there's still this enrichment, but it's no longer. Okay, yeah, I want to see what this. Oh, yeah, surprised at this. Bacillus subtilis also sim. Okay, it's gonna. Right, we are almost. Alright, there's Campylobacter, alright. Okay, right, we should do a little bit better job labeling these, but yeah, we see still see this big enrichment there, but stuff worries. Okay, let me let's go back to the E. coli example. So let's just add this line break there. Okay, attack. Okay, yeah. Loading the data using this new, this is nice. This is all much. Okay. Okay, let's not do this plot. Okay. Okay, yeah, let's label this. Okay, I just want to see. Okay, so what's this? Okay. Okay, so this maybe. Okay, so this maybe makes some sense in the sense. Alright, this one makes less sense. Okay. But alright, so these are the two KOs that are even in wild type -12, so this would mean in wild type we see a much shorter version of the gene than we would expect. But the first one actually we do see -12 and -11 in the sort of in the GMGC. So this one might indicate that this is not a very good KO to use for this. Yeah, for this purpose, right? That there's a lot of variation. Yeah, there's a lot of variation in this itself, right? So it goes from just right. Yeah. Oh, yeah, you can. Okay, so there's fair amount of But the other one seems less clear. Alright, yeah, the other one, yeah. Wait, what? This makes Okay, sorry, this makes no sense. Yeah. Oh, okay, yeah, no, it makes sense, sorry. I was, okay, so this makes sense because this is nucleotides. So, yeah, so this is nucleotides, so it makes sense, so because 638, so this is about 200 something. Alright, so this makes sense. And this, right, so these two small hits. Huh. Okay. To be continued. But what we see, to be continued because we're out of time, but what we see is that in the first case, in this we could probably see that there's a lot of variation here. Now that's right. Right, let's write some notes. Let's do this. Let's leave some notes for next week. Okay, so this was done. Yeah, so KO. Okay, let's clean this up. Alright, so this is still a bit messy, but okay, so we'll also recompute gene. we didn't have time to get to this today, but as reference for these guys. Okay, with that, we're finishing a little bit late today. So yes, so as you see, I just pushed everything onto GitHub, so everything's on GitHub. Yes, I'll be posting a little summary to the mailing list and recount a bit later in the week, so watch out for that. Otherwise, feel free to join the mailing list, join the Discord, or just say hi. And I will see you all next week.